All right, thanks everyone. Excited to be here to talk about verifiable decentralized event streams and how they unlock much more scalable architecture for decentralized data. A little about me, I'm a software engineer, background in databases and distributed systems, was tech lead on MongoDB's replication system for a few years, thinking about their single leader consensus algorithm. So been really thinking about data and distributed data for a while, kind of joined the whole Web3 space almost 3 years ago now, and been working on Ceramic, kind of decentralized data system, which builds on all these verifiable event streams, which we'll be talking about today. So the kind of problem that we're trying to solve is around scaling, bringing decentralization to data and sort of dealing with the scale there. To give you a little bit of a sense of what we're kind of talking about here, I did a little Googling before this and found that there's about a billion credit card transactions per day worldwide, 1 billion. Compare that to about 4 billion just posts on Facebook. There's about another 4 billion likes and comments, another 10 billion messages just on Facebook. So that does not include Instagram, any other social media sites, does not include the number of emails that are sent or non-social use cases. So you think about just the scale of the number of reads and writes for data that are happening, the number of data-oriented transactions online, it is a mind-boggling scale, far bigger than any sort of financial use cases. So if we can take some of the advantages that we've seen around decentralization that blockchains have brought to sort of the financial world and start applying those to data, the potential for transformation here is really, really quite huge. But with that huge difference in scale come scalability challenges, and blockchains are fundamentally limited in how much they can scale based on their architecture and the trade-offs that they're making to support the use cases they're designed for. So today I'm going to propose an alternate architecture built on event streaming that I think can provide many of the same benefits as blockchains, but be a lot more scalable by being more optimized for data. We'll talk a little bit at the end about some use cases around things like decentralized databases, which is something that Ceramic's very concerned about, and decentralized compute, which is obviously very relevant to this audience, and a little bit on some of the challenges of making this actually work. We all know data is really the foundation of modern applications. There's the popular saying, data is the new oil. So there's lots of businesses, whole companies where businesses around sort of extracting value from data. But we all know that data is a lot more useful when it is networked with other data. Single small pieces of data on their own are not very useful. The value comes from being able to correlate data and connect data and the sort of network effects around data when data can be shared and interoperate. This is what gives so much power to the big incumbent monopolies, the sort of Facebook, Google, Amazon. They have so much data and they're able to extract so much value from that, from the sort of network effects and the power of controlling that much data. But for anyone else, they're really cut off from this ecosystem because the data is siloed into these application silos. This is something that blockchains really help solve. Blockchains are these sort of open, interoperable systems, right? And the interoperability and composability of blockchains is really what we're trying to get after here. You see this happening in DeFi ecosystems, right? Where a new smart contract or a new DeFi protocol comes out and it can plug into the existing ecosystem of DeFi. You can take the outputs of one DeFi protocol and plug it into the inputs of the other. The whole collective ecosystem gets more powerful as each new protocol kind of comes online. That type of shared interconnectivity and interoperability and the sort of collaboration and innovation that unlocks is really powerful. And if we can bring that to data, that's really the goal that we're trying to achieve here. So then I think the obvious question then is, okay, so why not just use a blockchain? You can put data on blockchains. You just talked about how great they are. They do have some really nice properties. They provide this sort of decentralization, the sort of credible neutrality around not having a single party that controls it, the censorship resistance that data can't be withheld or tampered with, the attestations and provenance, knowing exactly who authored every piece of data, because you have cryptographic signatures over every transaction that introduces any data into the system. And this composability, that because everything is on this open, interoperable network, different apps can plug into each other's data, into each other's operations, and now data is no longer siloed to the individual app that was created through, but you have multiple apps that share and collaborate around user data. So these are all exactly the properties that we would want in a kind of decentralized data system. But the real problem is scale. Blockchains are fundamentally limited because of the design trade-offs they have to make to support what they were built for, which is really the transferable digital assets. So like tokens, cryptocurrencies, NFTs, that transferability requires the ability to prevent double spend. You want to make sure that you're not, sending the same token twice or sending the same NFT twice. And so in order to ensure that, if you're sending a token from account A to account B, you have to be able to update account A and account B atomically. This is sort of a single transaction that requires really strong consistency over the entire state of the ledger. And in order to do that, it basically means every node needs to process every transaction, which really limits the scalability and the throughput. So with a system that is optimized for data, we can make different trade-offs. We don't need to support transferability because most data is inherently soulbound, to kind of borrow that term, but basically means it's tied to an individual user, right? Like my profile is my profile. There's no need to ever transfer my profile to someone else. My posts are my posts. My messages to my friends are my messages. You don't need that transferability. And so by giving up transferability, we don't need double spend protection. It means we don't need this really strong consensus system. We can have eventual consistency and more targeted consensus around specific data sets instead of over the entire global state of the ledger, which will enable a lot more scaling. So let's talk a little bit about the architecture here, event streaming. I think probably I don't need to explain this as much to this audience. Probably a lot of people here are familiar with event streaming systems. Really been kind of battle-proven architectures from the Web2 world with things like Kafka and RabbitMQ, Spark, all these things that are really designed to operate at really, really large scale. Facebook, Twitter, really, really big scale. And by they work by separating the concerns between who's producing events that describe certain transformations to the state of the world, and then who has to take action based on those events. And that kind of separation of concern enables much more scalability and throughput. Event sourcing is the process of storing these events in a kind of a persistent log. It makes it easier to replay that log, to sync history if you're offline for a while, or to ensure these kind of at least once delivery semantics. You can kind of think of a blockchain as a verifiable, event-sourced event system with a single stream and infinite history. And so many of those properties are ones we would want to maintain in our decentralized event streaming system optimized for data. The key difference is instead of one big stream, we can have many, many smaller streams. And that's where the scalability comes into. So to sort of demonstrate this architecture, what this actually looks like, the event streams are a stream of signed updates. So each event can be, in the case of how this works for Ceramic, each of these events is actually stored on IPFS. So it's content addressed. You have a link to the CID of the previous event in the log. So you basically build a hash-linked, singly linked list. And then each event has a signature from a wallet or from a key, really, from any sort of private key system that signs that data, which both sort of serves two purposes. You kind of get that verifiability and tamper resistance, kind of the combination of the signature and the content address nature. The fact that signing the most recent event, because that also includes the hash link to the previous events, you're really not just signing the current event, you're actually signing over the entire history of the entire stream. And then from that signature, who's authoring that event, and that can be really useful for the access control rules. Each stream can have a controller of who's allowed to publish data, new events into that stream, and those signatures can be a part of those access control rules. You don't strictly need something like DIDs for the system to work. You could have streams that are tied to individual key pairs, but individual key pairs are brittle. So it's helpful to have some sort of abstraction in front of the key pairs, and DIDs are a really natural abstraction for this. So this is what Ceramic uses. This DID layer then allows you to have multiple keys that control a single identity, and it supports things like key rotation and key revocation for access to the data. By having multiple nodes that are syncing and serving these streams, you get decentralization and redundancy of this data, even if the data is just stored locally, but you can take it a step further and put that data onto decentralized storage systems like IPFS, Filecoin, Arweave, and others to even further decentralize the data and ensure the sort of redundancy and availability of the underlying event data. The immutable stream ID is, so every stream has, we call stream ID, which is how you identify that stream and look it up. And that's, really useful. We're relying a lot on kind of immutability and content addressing for some of the verifiable properties we want here. Each event itself is an object in IPFS, which is immutable and content addressed. But that immutability is challenging for when you actually want to be able to update data over time. If you have your website stored on IPFS, you uploaded a new version, now you get a new CID. Anyone who wants to find your website needs to somehow find out about the new CID. So it's helpful to have a single persistent identifier that doesn't update. So in the case of Ceramic event streams, the stream ID is is derived from the CID of the initial event in the stream. So the initial event in the stream kind of establishes the metadata for that stream, what data set it represents, who the sort of access control rules around who's allowed to publish data into that stream. And then from that encoded data, you get the persistent identifier that allows you to look up the stream even as new events are published into it. I think timestamping and ordering is a pretty interesting concept here. Time in a distributed system always gets kind of tricky. So the nature of the event stream itself, where every event is linked to the previous event, gives you really strong ordering guarantees within a single stream. It's very easy to tell whether any one event is before or after any other event in that stream. Ordering across streams gets a lot trickier. And that might be something that you might really want to do. Imagine that you actually have like a user account or identity that is represented by an event stream, where those events might be changes to the access control rules, right? Like an event might grant or revoke access to a given resource, or might add or remove a given key or set of keys from who's allowed to authenticate as that identity. So now if that, that account that's sort of being managed by one stream goes and then tries to publish events into a different stream, but maybe that access was actually recently revoked, you can start to see how the ordering of these events across streams becomes really important. So the way Ceramic approaches this is actually by leveraging traditional blockchains, basically using the blockchain as a big timestamping machine. Blockchains are actually pretty good timestamping machines, especially in a sort of trustless system like what we're trying to build here. Every block that's produced in blockchain has the block number, which is guaranteed by the protocol to be larger than any previous block that was produced. And many blockchains even take it a step further and actually encode a block timestamp, which is tied to sort of real-world wall clock time with some protocol level systems to protect against clock drift, things like that. So it's actually quite a useful metric for tracking the passage of time. So what we can do is take a hash of an event, publish it in a transaction on a blockchain, and then based on when that transaction gets included in a block, we can see that the event must have been created at some point before the hash of that event showed up on chain. And so it doesn't tell us exactly when the event happened, but it gives us a pretty nice upper bound, is that it must have happened before this timestamp. And then if you have data events that fall in between multiple time events that correspond to sort of blockchain transactions mined in particular blocks, it gives you a nice range that it must have been within this range. And that allows you to start doing some ordering of events across streams and synchronizing different events between streams. Of course, there's still the scalability concerns here of if you were submitting a single blockchain transaction for every event in all of the streams. Now we're kind of back to square one, but you can solve this with by bundling up multiple hashes into a single transactions with things like Merkle trees, make this much more scalable. And so lastly, and I think in many ways most importantly from the scalability story, is the fact that events are processed only by the nodes that care about those events for those streams. There's real work associated with processing these events. You have to discover the event, sync it over the network, validate the signatures, and if the actual events themselves describe some sort of state transition or some action that needs to be taken, do that. So the whole goal that we're trying to get here is that not all nodes need to process all transactions. That's how we're getting the scalability. So what we can do is allow nodes to subscribe only to the subsets of streams that are relevant for their use case, for the application that they're trying to support. So in this image, you can kind of imagine that maybe all of the blue streams are like streams of social media posts. Like these are all the tweets. Each user has their own stream for all of their tweets, say, for example. And maybe the red streams are like sensor data coming from weather sensors, some sort of decentralized network of weather sensors. Now, if you have an app that's trying to understand weather patterns, they can subscribe to the weather data streams and completely ignore the social streams and vice versa. And that ability to only subscribe to the data sets that you care about is where the scalability comes from. And this, of course, comes with the trade-off that you can't have any sort of transactional operations guarantees but that go across streams, or at least not very easily, not without doing a distributed transaction, which is slow and hard to scale. But within a given stream, you can have very strong guarantees around, like, if a stream represents a particular document or a particular data set, you can have really strong transactional properties sort of within the data governed by that stream, but not be able to do transactions across streams. And so that's what makes this system not great for like financial use cases, which a blockchain is better optimized for, but for this sort of non-transferable data where you don't need these sort of cross-stream transactions or cross-data set transactions, you get that scalability. So that's sort of the architecture. To talk a little bit about the use cases, big one for Ceramic and really where we came at for this whole architecture was decentralized databases. We really are focused on this idea of reusable and composable data, breaking down the silos around user data online so that users can bring their profile with them across applications, take their social graph with them across applications, bring their post, their history, all the aspects of their identity, and not have it be tied up into a single app, and not have to recreate your data every time you switch apps, not have this really high switching costs, but actually have really sort of frictionless motion across an interconnected app ecosystem because your data comes with you and it lives on this sort of open, verifiable network. And so that's kind of the use case that we really came at this from. And so what we're building right now, we recently, just a couple months ago, launched ComposeDB. It's a database built on top of Ceramic. It's a graph database, uses GraphQL APIs, so very like simple, intuitive APIs for developers to build on in a way that's very familiar to developers who are building Web 2 apps on top of like relational SQL databases or MongoDB or like any sort of traditional databases. You can have a lot of the features that you're used to around powerful queries, the ability to like query across the data set. You can think about the use case of like, okay, I want to build like a social feed. So I want, get me all of the posts and all the comments and likes on those posts by anyone that I follow. Like, it's actually a pretty complex operation, right? You have to go from the user to the list of all the people they follow. For the list of all the people they follow, you have to go to all of those people's posts. For all of those posts, you have to go to all of the comments on those posts, or all the likes on those posts, or the likes on the comments on those posts, and get all of that in a single query ordered by timestamp of, the original posts, and get that back in, milliseconds, right? To sort of have the performance characteristics that we expect for modern application development. And so to make that work, the way we kind of built this is we use Ceramic as a sort of almost like a bidirectional sync protocol to synchronize multiple individual databases. So you can run a database to support your app that then you configure which data models or like which data sets you want to sync and index. It uses Ceramic to sync that data locally, and then you have a very fast performant way to run queries across that data. But the Ceramic event streaming layer remains the source of truth. That's where every update to any data is represented in the individual events. And because it's in this sort of verifiable data structures, you can ensure that your local database that you've synced is truly in sync with the global state of the world, because you have these verifiable streams to show you that your current state is well synced with the state of the other databases that are accessing the same data set. So then sort of the next use case that is clearly very relevant to this crowd is around decentralized compute. Going sort of a level lower and not just thinking about interacting with sort of the database APIs that are built on top with Ceramic as kind of like the operation log, but instead actually going directly to the event streaming system, using it more like a decentralized Kafka, where you can sort of publish and subscribe to arbitrary events and then feed that into decentralized compute systems. So like this compute node in this diagram, that could be a Bacalhau node, or that could be a Fluence node, or any other of these sort of decentralized compute systems that are being built. You can have various data sources coming in these event streams and then feeding into these compute nodes that are subscribing to one or more event streams, doing some computation, and then potentially taking some action in the world, or even potentially outputting new data into new event streams as sort of the results of their computation, which even could then feed into further computation. I think where things get really interesting here is if that compute layer is itself verifiable, is built on a sort of verifiable compute system, then you can have an entire data processing pipeline from start to finish where the entire system is verifiable. You can see the source of every piece of data, how it entered the system, who published it, know the integrity of the data from the moment it was sort of published by the original author through every transformation it went through, every compute. You can see the compute and verify the computation that was done on it, and then verify the output that was outputted from that compute, and really be able to audit and trace the entire path of the computation from start to finish. So this, I think, is really the kind of longer term vision for Ceramic. Like right now, so far, we've really been focused on this sort of database, how to make it easy for application developers to have sort of like a Web 2 database-like experience, but where that data is open and interoperable and composable with other applications, and kind of just using the event streaming system kind of under the hood to power that. But I think over time, we hope to expose a lot more APIs to access the event streaming system directly and use it much more just like as an event streaming system, which then could enable a lot of these types of use cases as well. Some challenges to really making this actually work at scale. We talked a lot about, for the scalability story, the independence of these streams is really important, that the reads and writes to one stream don't impact other streams that are on unrelated data sets. This sort of architecture where we have lots of little streams that can be tied to individual data sets or data models enables that type of separation, but actually doing that in practice and actually making sure that impact is minimized, there's still challenges there. So like, for instance, right now, every update to every stream on Ceramic is published into a single shared pub subtopic built on the P2P gossip sub. That obviously won't scale. That completely defeats the whole purpose of nodes only deal with the data that they care about, because right now every node receives every event to every stream. Clearly that's not going to scale. So what we're working on right now is a new stream synchronization protocol, off of some work on decentralized set reconciliation systems that we've done some research on. Basically, that will be a way to register in the DHT which data models or data sets you're interested in, and then synchronize, sort of do a way to figure out what data you have, what data the other person has, and bring them into synchronization in an efficient way. And so then, of course, the next problem becomes the DHT. right? The routing layer of how do you actually discover, okay, like I'm interested in syncing all of the weather data or all of the user profiles. How do I discover the other nodes on the network that have that data so that I can sync from them? That discovery and routing system really becomes the bottleneck. And I think that that is ultimately the bottleneck in this system, is that DHT. Thankfully, you know, we are not the only ones thinking about scaling DHTs. There's a lot of smart people working on that problem, including probably some people in this room. So, you know, I even heard someone yesterday talking about like hierarchical DHTs and other sort of DHT scaling solutions. So there's a lot of work being done across the whole space on this problem. So by the time we get to the scale where that starts being the bottleneck, I'm sure we'll be in very good company with lots of people working on scaling that. And then lastly is like, what if one stream just gets really big? At that point, if one stream has a lot of writes, now you're kind of back to the blockchain kind of world, right? Of one really big stream. And yeah, like that is a problem. If one stream gets really big, you can start to look at, you know, blockchain. Some of the same scaling solutions that are being explored in the blockchain space can probably be applied here as well. But I think the key that we have as an advantage compared to, you know, just having the blockchain system is this ability to split data up into smaller streams and sort of partition it across lots of smaller independent streams. So as much as possible, like that is the key new tool in our tool belt for helping deal with scalability challenges, while still maintaining the verifiability, decentralization properties of the traditional blockchain world. If any of this sounded at all interesting, encourage you to come join our community. That QR code will take you to our Discord. We talk, you know, a lot of work on the event streaming system, decentralized databases, verifiable, composable data. If any of that gets you excited, please come talk to us. I'll be hanging around later today as well. And yeah, it looks like I've got about 2 minutes if there's any questions before we all go to lunch.
Would just using this as a notary, like open timestamps using your system, would that be overkill to just use that feature? Or should we stick with things that are pure notaries for cryptographic notarization?
I guess it sort of depends on the use case. I don't know if I can give a blanket statement. So like if using this for notarization, you mean like around like the cryptographic signatures to sort of see, yeah, I mean, it kind of depends on your use case. I would say the advantage of like, you can always just sign some data and have that kind of signature there. The question then is what do you do with it at that point? Like I think what's and the time stamping, right? Okay, so yeah, for the sort of blockchain timestamps, yeah, I mean you could do the same thing like what we do, right? Put a hash on chain, and then have that sort of be able to point to when that that hash showed up on chain as a timestamp. I think what Ceramic provides on top of that is around the data discoverability, is sort of having a catalog of data sets that are tied to specific schemas and data models, and you can say like, okay, I want to sync and index all of the data with this schema or within this sort of data model data set. So like that discoverability element, and then just like easier APIs for application development. Yeah, that's the real extra layer on top.
And then could you go into over again or into a little bit more detail, sort of cross-stream synchronization? You said it's a difficult problem to solve. Can you give us a feel for sort of how well Ceramic solves it as a protocol and how much would have to be brought into the system?
Yeah, so let's see if I can go back to this little image here. So about cross-stream synchronization. So this diagram, I didn't like totally break it down, but it sort of shows you have data events, which are like the regular events that are being input into the stream, and then time events. Time events link to basically link to a blockchain transaction that shows when the hash of the event was published on chain. That gives you a bound on when that event was published. So it's not perfectly precise, right? Like it depends on how frequently these anchor timestamps are being created. Right now we get, the exact rate of these time events happening for us fluctuates a little bit based on usage, but it's somewhere in the order of like 10 to 20 times per day. We are sort of, but like as the number of writes in the system increases, the rate of anchoring will also increase. Like we're just doing it for cost-saving purposes. We only publish it once we have enough writes to make it worth it. So like right now, it's once every few hours you get a timestamp. As the usage of the network increases, I expect that to go down to minutes eventually over time. So it kind of depends a little bit on the granularity that you need. But if you needed, so like you can still have ties, of course. Like if you have two different streams that create a new event within a couple minutes of each other, they might both get anchored to the blockchain in sort of the same blockchain transaction. So you don't really know the relative ordering if they're anchored in the same Ethereum block. But for bigger differences in time, they'll wind up in different blocks, and then you'll have that ordering. So it kind of depends on your needs around what kind of granularity you need.
Are you using the same blockchain to anchor all streams? Or is
Yes,
okay.
we are using the same blockchain to anchor all streams. We use Ethereum L1 right now. At some point, we'll probably move to an L2, but it is important to minimize the number of chains that we support, both just for the complexity of the network, so because you need every node to support every chain, but also, ordering across, like if one stream is anchored on one chain and one stream is anchored on another chain, it's no longer really an apples-to-apples comparison for that ordering. All right, lunchtime.